Hello students, today I'll be speaking on the topic elimination reactions. Before I come directly to elimination reactions, I would like to enlighten you with a brief introduction about organic reactions and the reactions that organic compounds undergo in order to form different products. Organic compounds, or in other words, compounds of carbon, can undergo many different types of reactions. And this chemical reaction is simply represented by a chemical equation. That is, A and B react in the presence of X to give C and D as products. A and B are the initial substrates or the reactants, X is the reagent, and C and D are the final products. This chemical equation really indicates how the reaction proceeds in actuality. So the actual steps by which a reaction takes place, whether through a transition state leading to an intermediate, which can be real or postulated, or directly via an intermediate, or through a simple single step or a complex multi-step process to give the final product, is systematically given by a reaction mechanism. So reaction mechanisms are in general theories that have been devised to explain the facts which have been obtained experimentally. But one should also keep in mind that the interpretation of experimental data may not be clear-cut. That is, several mechanisms may appear to fit a chemical reaction perfectly well. So, the reaction mechanism which is accepted for a particular reaction as the right one is when it has the strength to be used to make predictions which are borne out in practice. This means that when you do or perform a particular reaction in actuality and you know the products, and if you fit in this reaction mechanism and predict the products, and if the predictions and the real products, they match, then that particular mechanism is the right one for that particular reaction. So now, based on the types of reaction mechanism, organic reactions can be classified into 5 main categories. They are substitution reaction, addition reaction, elimination reaction, reduction, oxidation or redox reaction, and lastly, rearrangement reactions. Sometimes, based on authors' preferences, pericyclic reactions, they are also included under rearrangement reactions, or whether it is completely studied as another type of organic reactions. So out of these 5 and 6 types of organic reactions, today I'll be going to talk about elimination reactions and the different categories of elimination reactions, their mechanisms involved, the orientation and stereochemistry involved in these reactions, and how elimination competes with substitution reactions, including different factors affecting such type of elimination reactions. So let us begin with the definition of elimination reactions. Elimination reaction is an organic reaction which involves the removal of 2 atoms or groups from a molecule, that is the substrate, without being replaced by other atoms or groups, resulting in the formation of multi-bonded, that is double or triple bond, or ring compounds as products. The most common elimination reactions are those involving the loss of atoms or groups from carbon atoms. So you have one group being lost from one carbon atom and the other group being lost from another carbon atom, which can be adjacent or a bit farther away from the first one. Eliminations from atoms other than carbon atoms are also known. These are also included under elimination reactions. For example, we have the removal of one group from nitrogen atom of oximes and another group from carbon atom to give nitriles. Then we also have another example for the removal of HCN, that is hydrogen cyanide, from cyanohydrines. That is, the hydrogen atom from the oxygen atom is removed to give carbonyl compounds. So based on the starting material, it can be an aldehyde which is formed or a ketone which is formed. Besides this, elimination reactions can also be divided into different types based on the position of the living groups. So these are grouped under number 1, 1,1 elimination reactions or alpha elimination reactions. So what are these type of alpha elimination reactions? These reactions or these elimination reactions are those when two atoms or groups are removed from the same atom. It can be either carbon or it can be some other group. For example, when you remove or eliminate hydrogen chloride from one chlorobutane to form one butene in the presence of a strong base via the formation of a carbene intermediate, that is an electron deficient carbon center, this is an alpha elimination reaction. The next type of reaction, elimination reaction, based on location or position of the living groups is the 1,2 elimination reaction or the beta elimination reaction. In beta elimination reactions, what happens is that two atoms or groups are removed from adjacent atoms. Beta elimination is the most common type of elimination reactions. For example, beta eliminations can include base-induced dehydrohalogenation of alkyl halides. For example, if you look at this figure, you will see that a molecule of hydrogen bromide, HBr, is being removed from the alkyl bromide to give the alkene product. This also follows beta elimination. As you can see, the two groups are removed from adjacent carbon atoms. The next example is acid catalyzed dehydration of alcohols. This is also a very good example for the formation of alkenes. So in this elimination, removal of a molecule of water after protonation of alcohol to give the alkene product is observed. Then another very important example is the Hofmann degradation of quaternary alkyl ammonium hydroxides to give alkenes. Here also, the product that is formed is the alkene, and this follows beta elimination. Another type, or the third type of elimination based on position of the living groups is 1,3 elimination reaction or gamma elimination reaction. In these type of elimination reactions, there is the loss of one atom or group from the atom bearing the living group X, as is seen in the picture, and we consider it to be the first atom. And then there is the loss of the second group or the atom, which is usually a hydrogen atom, from the next to next, that is the third atom from the first, to give the 1,3 cyclic compound. The examples of these type of gamma elimination reactions, they include a small part of the Favovsky rearrangement of alpha haloketones to give cyclic propanone intermediate. The cyclic propanone intermediate then can undergo different types of addition reactions in order to give the final rearranged product. And there are also different types of 1,4, 1,5, and 1,6 elimination reactions where the positions of the living groups are far apart from one another, and all these reactions lead to cyclization. And these products are usually cyclic compounds. So among all these elimination reactions, which are based on location and position of the living groups, the 1,2 elimination or the beta elimination is the most common and the most important elimination group amongst organic reactions. So in 1,2 elimination reactions involving carbon atoms, the atom from which the living group Y is lost is usually designated as 1, or the alpha carbon atom, as seen in the figure. And the other carbon atom, which bears the second group, which is usually a hydrogen atom, is called 2, or beta carbon atom. These 1,2 elimination reactions are simply referred to as beta elimination reactions by just omitting 1, or alpha. So in all this remaining talk, I'll be using beta eliminations to denote 1,2 elimination reactions. So based on this mechanistic pathway, that is how the reaction is actually taking place in a stepwise manner, these beta eliminations can be divided into E1, that is elimination unimolecular, number 2 E2, that is elimination bimolecular, and number 3 E1CB, that is elimination unimolecular from conjugate base. So now I will start explaining one by one the different types of elimination reactions based on their mechanistic pathway. So first we start with E1 elimination reaction, that is elimination unimolecular. The mechanism is such that E1 is a beta elimination reaction in which the hydrogen-carbon bond and the carbon-Y bond, that is the carbon leaving group bonds, they are broken separately in two steps. That is, one step involves the formation of a carbocation intermediate, and then the next step ultimately leads to the formation of an alkene product. That is, if you look at the figure, the step 1 has the carbon leaving group bond, that is the CY bond, being broken first to form a carbocation intermediate. This step is slow and it's rate limiting and involves one substrate, and therefore you have the name unimolecular in E1 mechanism. Then step 2, this is a rapid non-rate limiting second step whereby a beta hydrogen is lost from the carbocation by base abstraction to give the overall alkene product. So the E1 reaction follows first order kinetics, and the overall rate of the reaction is determined by the slow first step, which is dependent on the molar concentration of the substrate but not on the base concentration. That is, it is independent of the base concentration that is being used in this particular reaction. Thus, it is a unimolecular reaction, and the rate of an E1 reaction is given as the rate is equal to K into the molar concentration of the substrate or the reactant that is being used. And K, small k, is the rate constant. A very good example of an organic elimination reaction where E1 mechanism is being followed is the dehydrohalogenation of tertiary alkyl halides. If you look at the figure, you will see that in the dehydrohalogenation of tertiary butyl chloride, in the presence of ethanol, the first step is the slow rate limiting step of the departure of the chlorine atom with the bonding electron pair as the chloride ion. And it forms a stable carbocation intermediate which is tertiary in nature. This tertiary carbocation is stabilized by the presence of the three metal groups which are electron donating, and therefore the second step, that is the fast abstraction of the beta hydrogen atom by the solvent molecule or by the base that is being used, followed by the subsequent movement of the electron pair to develop the carbon-carbon double bond and form the final product 2-methylpropene. So ultimately the final product is an alkene 2-methylpropene, and the mechanism is an E1 mechanism. So to understand the salient features again, we will summarize it as E1 reaction mechanism to be, number 1, non-concerted. That means it does not happen at the same time. That is, two steps are occurring and it is a two-step reaction mechanistic pathway. The first step is slow and it is rate determining. It is the removal of the leaving group with the electron pair, and hence a carbon cation intermediate is formed. The second step is a fast non-rate limiting loss of the second atom or group. In this case it is usually a hydrogen atom, to form the double or the multiple bonded product, and here also it is favored for tertiary leaving groups. Then number 2 point that needs to be remembered for E1 mechanism is it is non-stereospecific. That means the product that is formed following E1 is Sedzev rule. That means the more substituted alkene is the major product. Then number 3, it is unimolecular in the sense that the rate of the reaction, E1 mechanism reaction, depends on the concentration of only the substrate, and kinetically it follows first order kinetics. Number 4, the reactivity that is being followed for alkyl halides to undergo E1 elimination reaction is that tertiary alkyl halides, they have a greater reactivity towards E1 mechanism than secondary, than primary alkyl halides. In most cases, simple primary alkyl halides do not undergo E1 elimination reactions. And if the structure of the reactant or the substrate permits, that is, there is the presence of multiple beta hydrogen atoms in the reactant, then rearranged products can be formed due to rearrangement of the carbocation intermediate. The rearrangement of the carbocation intermediate happens in such a manner that the most stable carbocation is being formed. And then there is the abstraction of the beta hydrogen atom from the most stable carbocation, and therefore it can give rise to different products based on reactivity. Then the last one is that strong acids can promote the loss of the hydroxyl group as water or the alkoxy group as alcohol if the tertiary or conjugated carbocation can be formed. That means the living groups can be first protonated and can be removed as the protonated product in order to get the carbocation. So the next type of elimination reaction that we are going to discuss now is the E2 elimination, that is elimination bimolecular. So the mechanism in this type of beta eliminations is that they involve a concerted single-step process, that is only a one-step process, to form the corresponding alkene product. And the difference here is that it has to form this product after passing through a single transition state. So if you look at the figure, you have the reactant and the base, they combine and it goes through this transition product. Then there is the movement of the living group and formation of the final product in a single step. This single step proceeds in a manner that first the base pulls the proton away from the beta carbon atom, and simultaneously the living group departs with the electron pair through the transition state to form the alkene. A very good example of E2 mechanism is again dehydrohalogenation of alkyl halides. And in this case, we will be talking about secondary alkyl halides because they have a tendency to undergo E2 elimination reactions in a very detailed manner. So if we take the dehydrohalogenation of alkyl halides, which is secondary nature here, in the presence of sodium ethoxide ethanol mixture, we find that if you look at the figure, it forms 2-bromopropane gives propene by E2 mechanism. E2 mechanism follows second order kinetics, where the overall rate of the reaction depends on the single concerted step and is proportional to the concentration of both the reactant and the base that is being used. So the overall rate of an E2 elimination is given as rate is equal to K into molar concentration of the reactant into molar concentration of the base that is used. The base that is used in E2 mechanism is usually a nucleophile, that is, which has more capacity to donate the electron pair, and the strength of this nucleophile determines the rate of the E2 elimination reaction and follows the order amide or the NH2 minus azonide ion having greater power or strength than an alkoxide ion than a hydroxide ion. So now let us try to summarize the salient features of E2 mechanisms that we have studied so far. The first one is that E2 elimination reaction is concerted, that is, it's a single step. All the bonds formed and break at the same time and forms the alkene product. Number two, rearranged products are not formed since we have a single step and it provides no opportunity for the rearrangements of products. Third, it is stereospecific, that is, it is anti-periplanar geometry is preferred, while syn-periplanar geometry is also possible in E2 cases. This particular topic will be discussed in another video. Then another one is bimolecular, that is E2 reaction is bimolecular, that is the rate is second order depending on the concentration of both the base and the substrate. And lastly, it is favored by strong bases which act as better nucleophiles. In E2 elimination reactions, the orientation of the products, they follow both Sedzev and Hofmann rule. That is, it is a mixture of both the Sedzev and the Hofmann products. This is usually found in those type of reactants which have more than one beta hydrogen atoms. The percentage of such products depends on the nature of the living groups and the structure of the base that is used in this particular reaction. Now we come to the third type of elimination reaction based on mechanistic pathway, that is the E1CB reaction, elimination unimolecular from conjugate base. E1CB reactions are those beta elimination reactions which occur when the carbon-hydrogen bond is broken first to form a carbanion intermediate. Then it is followed by a second step whereby there is a loss of the leaving group to form the product alkane. The leaving group takes away the electron pair with it. Thus, the E1CB reaction mechanism can be described as a two-step process as shown in the figure. The first step is the fast reversible abstraction of the beta hydrogen by the base to form the carbanion intermediate, and this is followed by the second step, which is slow and rate limiting with the loss of the leaving group taking the electron pair to give the product alkene. So thus, the E1CB reactions follow the second order kinetics having the rate law. The rate of the reaction is equal to K into the molar concentration of the reactant into the molar concentration of the base that is being used. A very good example in this case also for E1CB mechanistic pathway is the dehydrohalogenation of primary alkyl halides. What we should remember here is that primary alkyl halides, they do not give elimination products using E1 mechanistic pathway. But if we use a particular substituent which can stabilize the carbanion intermediate, then it goes through E1CB pathway. For example, if we have 1-bromo 2-phenyl ethane in the presence of ethoxide ethanol mixture as seen in the figure, we get the substituted ethene. Another example of E1CB reaction is benzene formation, which is very important as benzene is a very important intermediate and many different reactions can proceed from the benzene intermediate. Here, the removal of a proton to form the carbanion by the base is the first step, followed by the loss of the leaving group with the electron pair to form the benzene. This can be attacked by other groups to give addition products as seen in the figure. Another example where E1CB elimination mechanism is followed is the formation of carbonyl compounds from cyanohydrines. Here, there is the elimination of HCN from the cyanohydrine to give the carbonyl compound. So summarizing the salient features of E1CB, we have number 1, that E1CB is a two-step base-induced beta elimination reaction. The first step is fast and reversible, and the second step is slow and rate limiting. It has been found to follow second order kinetics, that is the rate depends on both the concentration of the reactant and the base, and here there is the similarity with E2 elimination reactions. That is, both reactions, whether it be E2 or E1CB, they cannot be kinetically distinguished. Another point here is that the E1CB is designated as such because the conjugate base of the substrate is formed first. That is, the carbanion of the substrate is formed first, and then it is followed by the departure of the leaving group from this conjugate base. So you have E1CB. And lastly, there are very few organic reactions which follow E1CB mechanism. That means it is not quite common. Now we have come to the end of this lecture, and the next lecture I'll be talking about elimination reactions based on stereochemistry, orientation, and how elimination competes with substitution reactions and the different factors that affect this type of competition. Thank you.